Previously, we have talked about the system of linear equations and what they represent, and we have seen that linear equations represent either straight lines or flat surfaces, depending on the number of dimensions or the number of variables involved with the equations. So in a two-dimensional plane, the linear equations would be representing straight lines, and in a three-dimensional or higher dimensional space, then these linear equations would be representing flat surfaces or planes. And then we also discussed about the solution to these linear equations, and that is, when we solve these linear equations, what is it that we are exactly trying to find? Of course, we are trying to find out the values of x, y, and z that would be, or the variables in general, that would satisfy all the equations given in that set of linear equations. But what do those values of x, y, and z represent? They represent the point of intersection of those planes or of those lines in the plane or space. So the solution that we are trying to find out is nothing but the point at which the surfaces or the lines are intersecting and meeting each other. So that is the solution that we are interested in finding. And previously we have also discussed about how to check whether a set of equations has a solution or not, and in that context we discussed about the determinant of a set of a matrix. So we talked about determinant, and how do we find the determinant? We first write the coefficient matrix of this equations, of the set of equations that we have, and then compute the determinant of the matrix, and then say that if the determinant, let's say of the matrix, if I call the matrix as A, if determinant of the matrix A is equal to 0, then the matrix is singular. And if our coefficient matrix is a singular matrix, then there is no solution or there is no unique solution. So there is no solution, in which case that means the lines or the planes do not intersect at any point. So that means all the lines or all the planes do not have a common point of intersection. In this case we say there is no solution or there is no unique solution. There is no unique solution. That means it is possible that they intersect at multiple points. That happens when the lines or planes are coinciding with each other. So we talked about both these cases in the previous video. And then I also talked about finding the transpose of a matrix. So that was another thing we did. Transpose of a matrix. So how do you find the transpose of a given matrix? You just interchange the rows and columns. So transpose means make the rows as columns, and that will, or equivalently you have to say that you make the columns as rows. So you interchange the rows and columns. That gives you the transpose of a matrix. Again, we will use this in our calculations later on, but we had done up to this point in the previous video. Today I will continue this and take you further into the discussions beyond the last video. And for that I've used an example here where we have a set of linear equations. It's a set of simultaneous linear equations. The first thing we are going to do is we will see how to represent these linear equations as a single matrix equation. So we'll first write the coefficient matrix of these equations, and if you recall from the previous video, the coefficient matrix is nothing but writing the coefficients of the variables x, y, and z in a matrix form. So in the first equation, the coefficient of x is 1. In the first equation, the coefficient of y is -1, and the coefficient of z is 3. So it's 1, -1, 3. Similarly, for the second equation, the coefficient of x is 4, and for y it's 2, and that of z is -1. And the third equation has 1, 3, 1. So that's our coefficient matrix, which we will call or denote by the letter capital A. Okay, and then we have our set of variables, the variables that we are interested in solving, that is x, y, and z. So we will write those variables as a vector of variables. So we'll call it small x, small y, and small z. So we have written that in a vector form. And then on the right side of the equation, we have these constants 5, 0, and 5. That is the values that the solutions give. The values of x, y, and z. When you substitute in this equation, it should give those values. So for this set of equations, that happens to be it's 5, 0, and 5. So we have a set of linear equations now represented as a matrix. So the coefficient matrix, we'll call it or denote it by the letter capital A. The vector of variables, we'll denote it by the letter capital X, and the vector of these numbers on the right side of the equation, we'll call it as the letter small b. So these set of equations can be represented as Ax equals b. Okay, and for much of today's video, we are going to focus only on this matrix A. So we are going to focus on this matrix A, and we'll again demonstrate or check first of all whether a solution exists for this set of equations. And for that, we will compute the determinant of the matrix A and check whether it is 0 or not. If it is 0, it means that these set of equations have no solution, have no unique solution. If it is not equal to 0, then we can proceed with solving the A set of equations. But before we even go into solving these equations, we are going to just focus today on this matrix A and some of the calculations that we will perform on this matrix A. So our focus for today's lecture would be only on the matrix A. So let us quickly find the determinant of the matrix A and see what we get. So the determinant of A, so we'll write it as determinant of A is equal to, and I'm going to use the first row in computing the determinant. So I'll use this row. So it is 1. So the first element here is 1. And then we close out the row and column. So the row is the first row and the first column where that 1 is present. So we close that. So we are left with these 4 numbers, which is 2 minus 1. So we call that as the cofactor. 2 minus 1, 3, 1. So, okay. And then we have the positional sign of the next number. So it's plus, minus, plus, minus, plus, minus. So the positional sign for this is minus. So we'll have to put that minus, and the value of the element in that position is minus 1. And then we will close the row and column in which that minus 1 is present. So we close this first row and the second column where this minus 1 is present. So we are left with 4 minus 1, 1, 1. So we'll write those numbers. 4 minus 1, 1, 1. And the positional sign for the next element is plus. So it's plus, minus, plus. So we'll put that plus. So we get plus, and the element there is 3. And again, we will close the row and the column in which that number is present. So the first row and the third column. So we are left with these 4 numbers, 4, 2, 1, and 3. So we'll write it as 4, 2, 1, and 3. Okay. Once we have written this, we can now, so I'm going to make a demarcation here like this and continue over here. So we can write that as 1 into, and now we do the cross multiplication. 2 into 1 is 2, minus 3 into minus 1 is minus 3. So it will be 2 minus 3, which is 2 plus 3. Minus of minus 1 will become plus 1. And again, we do the cross multiplication here. 4 minus of minus 1 will become 4 plus 1. So into 4 minus of minus 1. So that's 4 plus 1. Plus 3 into, again, when we do the cross multiplication, it's 4 into 3 is 12. Minus 1 into 2 is 2. So we get this. So we get it as 1 into 2 plus 3. So it's 1 into 5 is 5. plus 1 into 5 is also 5, and 12 minus 2 is 10, into 3 is 30, so plus 30. So we get the determinant value as 40. So the determinant of the coefficient matrix of this set of equations, so the determinant value of this matrix is equal to 40, which is not equal to 0. So therefore the matrix is not singular, and therefore there is a solution. So it's not singular, therefore solution exists. So we know now that this set of equations has a unique solution, and we can proceed with solving and finding the solution for these equations. Now, before we even solve these equations, let us have a pictorial view or a graphical representation of these equations and see exactly what is it that we are trying to find out. So if you see from this plot that I have made on the screen, the first equation is represented by this green surface. So the green surface here is representing the first equation. It is a flat surface. It's like a piece of paper in the three-dimensional space, right? So the first equation is represented by this green surface. It's a two-dimensional plane in a three-dimensional space. Similarly, the second equation is represented by the red plane or the red surface, and the third equation is represented by this blue or violet surface in this three-dimensional space. And what we are trying to find by way of solving these equations is to find the values of x, y, and z that would satisfy all the three equations. That means that point should lie on all the three surfaces. The value, that point of x, y, and z, the point corresponding to the solution of x, y, and z, should be present in all the three surfaces of planes. And that would mean that the point is nothing but the point of intersection of these three surfaces, which is exactly here. So that's the point at which the surface represented by equation 1, the surface represented by equation 2, and the surface represented by equation 3. So the green, red, and violet, all three surfaces, they meet at this point. That is where they intersect. So the values of x, y, and z that or the point that will lie on all these three surfaces is exactly this particular point here. Okay, so let me quickly mark that. So that's our solution. Okay, and if you notice it, that solution is going to be x equal to 0, x equal to 0, y equal to 1, and z equal to 2. So that's our solution in terms of a point in the three-dimensional space, where we can write it as x comma y comma z. We'll write it as 0, 1, 2. So that's our point. So you can clearly see here the red axis is the x-axis, the green axis is the y-axis, and this blue axis is the z-axis. And this point here, you can clearly see that on the z-axis it is lying at 2, so z equals 2. On the y-axis it is lying at 1. It is lying at 1, so y equals 1. But what is not very obvious here is that is the value of x being 0. So that is not very obvious from this diagram, but I will show it in a separate diagram in the next slide. But the value of x is 0 because if you see this particular point, it is actually lying on this wall. If you look at this three-dimensional space as a room, so what I have marked here, this is a wall in that room, and this is, say, the width of the room, and this is the height of the room. So you have the y-axis representing the width of the room, the z-axis representing the height, and the x-axis representing the length, for example. Now, this point of intersection is lying on one of the walls. Okay, it's in the YZ plane. So the value of x is 0 because it's not in the middle of the room. It is lying on one of the walls of the room. So therefore one of the axis values is 0. In this case it happens to be the x-axis value is equal to 0. I will show it from a different perspective. I will show this diagram from a different angle and prove this point. But the solution, when we solve it, we will get this answer of x equal to 0, y equal to 1, and z equal to 2, which you can also verify by substituting in these equations. When you substitute these values of x, y, and z in all the three equations, the equations will be satisfied. So that is the solution. So in terms of the graphical representation, it is the point of intersection, and in this particular case, that point of intersection happens to be on one of the walls, on one of the walls of the room, if you look at this three-dimensional space as a room. Let us now look at these equations, or the planes that these equations represent, from various perspectives. So I'm going to play this video, and at some point I will pause it and show you where the solution exists. So we are seeing it in a three-dimensional space now, and the point of intersection is the point which I pointed out earlier, where all the three planes are intersecting. Now what we'll do is we will look through one of the axes so that we can see only the remaining space only as a two-dimensional. So let us see here where I'm taking the x-axis and fixing the x-axis, or looking through the x-axis now. Now in this case we clearly see that the values of y and z are occurring, or the point of intersection that we see here is lying at y equal to 1 and z equal to 2. So the point of intersection that we see here is lying at y equal to 1 and z equal to 2 when we look at this in a yz plane. Okay, if we look at this three-dimensional space through the x-axis, that means we are going to see only the y and z axis, okay, because the x-axis, the red point, is now perpendicular to us, so to the screen. So therefore we don't see it now. So we are seeing here only the y and z axis, and the point of intersection is happening at y equal to 1 and z equal to 2. Similarly, we'll change the perspective and look at it from a different perspective, perpendicular to some other axis. So here we are looking perpendicular to the y-axis. That's perpendicular to the y-axis. The green axis is the y-axis. So I'm going to make this projection of the screen perpendicular to the y-axis. Let me go back to that. Right, we are now here almost perpendicular to the y-axis. So what we see on the screen here is the x-axis and the z-axis. So in the xz plane, we see that the point of intersection is happening at x equal to 0 and z equal to 2. So the three planes are intersecting at x equal to 0, z equal to 2, and similarly we will now see perpendicular to the z-axis. So we now have it perpendicular to the z-axis. So we clearly see that the point of intersection is happening at x equal to 0 and y equal to 1. So when we are looking at when the z-axis is perpendicular to our screen, then we clearly see that the point of intersection is happening in the xy plane at x equal to 0, y equal to 1. So putting all this together, we see that the solution lies at x equal to 0, y equal to 1, and z equal to 2. So that is our solution that we are interested in finding. And we will now look at some of the steps involved in solving these equations by the first method that we are going to use to solve them, which is called as the matrix inversion method. So let's play out this video and finish it off. So we see that the solution is nothing but the point at which all the three flat surfaces or planes intersect with each other.